In 2021, the United States Department of Energy made a quiet announcement that almost nobody outside the hydrogen industry noticed. They set a target, a benchmark for how efficient hydrogen production needed to become before green hydrogen could compete on cost with fossil fuels. The number was 77% electrical efficiency. The deadline was 2031. That was the plan. A decade of research, a decade of funding, a decade of iteration, and by 2031, maybe, just maybe, green hydrogen would be ready to scale. It is now 2026, and a startup out of MIT says it has already hit that number. Not in a simulation, not in a model. In tests with real partners in real conditions, their electrolyzers are running at the efficiency the DOE said wouldn't exist for 5 more years. And here's the thing that should stop you cold. Hydrogen was never waiting for 2031. The industries that need it, steel, ammonia, aviation, heavy freight, have been waiting for decades. The technology just couldn't meet them. Now, for the first time, it might. So here's the question this video is going to answer. And it is not the question you think it is. The question is not whether this breakthrough is real. It appears to be real. The question is, if the machine just got dramatically better, why isn't green hydrogen already winning? To understand what just happened, you need to understand what an electrolyzer actually does and where it has been losing. Hydrogen is the most abundant element in the universe. It is everywhere. The problem is that on Earth, it almost never shows up alone. It is locked inside water molecules bonded to oxygen. To get it out, you have to break that bond, and breaking that bond requires energy. The electrolyzer is the machine that does this. You run an electric current through water, the bond splits, and out comes hydrogen gas on one side and oxygen on the other. Clean input, clean output. No carbon, no combustion, just electrochemistry. In theory, this is the cleanest industrial process imaginable. In practice, it has been bleeding efficiency at every step. The core problem is not the water. It is not the electricity. It is a membrane, a thin, chemically engineered layer sitting at the heart of the electrolyzer. Its job is to let hydrogen ions pass through while blocking everything else. It is the filter that makes the whole system work. And it has been leaking performance for decades. Every time a hydrogen ion, a proton, tries to cross that membrane, it encounters resistance. Not mechanical resistance, electrochemical resistance. The kind that converts useful energy into waste heat instead of hydrogen output. The kind that forces the system to consume more electricity per kilogram of hydrogen produced. The kind that, at commercial scale, turns a promising economics model into an unworkable one. Here's the number that defines the entire industry's problem. At $5 per kilogram, green hydrogen fails. At $2 per kilogram, entire industries flip. Steel decarbonizes. Ammonia goes clean. Aviation finds its fuel. The gap between those two numbers is not a policy problem. It is not an infrastructure problem. For years, it has been a membrane problem. That resistance is why green hydrogen has cost $4, $5, $6, sometimes $8 per kilogram, while gray hydrogen, that's made from natural gas with full carbon emissions, has sat comfortably below $2. The machine was working, the membrane was losing. This is where 1S1 Energy enters the story. The person who cracked this problem was not supposed to be working on hydrogen. Dan Sobek spent years at MIT studying aeronautics, then mechanical engineering, then electrical engineering, and computer science. His doctoral thesis was about measuring the optical properties of biological cells, a technique for detecting disease by shining light through tissue at high speed. It was elegant, precise, and completely unrelated to energy infrastructure. What it taught him was microfabrication, the manipulation of materials at scales measured in micrometers, the chemistry of surfaces, the behavior of ions moving through engineered structures, skills that live at the intersection of biology, physics, and material science. And that the hydrogen industry, dominated by electrochemists and process engineers, had largely never imported. The person who solved the membrane problem wasn't a membrane expert. He was someone who had spent decades learning how to move charged particles through matter with precision, in a completely different field. When he looked at a proton exchange membrane, he didn't see an electrochemistry problem. He saw a materials problem, and that reframe changed everything. Around 2013, Sobek started asking a different question. Not how do we build a better electrolyzer, but how do we build a better membrane, the component that everyone in the industry was treating as a given. He brought the question to his co-founder, Sukanta Bhattacharya, a materials scientist. Sobek asked what could actually improve the efficiency and durability of a proton exchange membrane. Bhattacharya gave him a one-word answer: boron. The chemistry here is precise and worth understanding because it is not magic. Boron can be given a negative charge. Hydrogen ions, protons, carry a positive charge. Opposite charges attract. When you build a membrane with boron functionalized polymer chains, you create a material that actively pulls protons through, rather than simply tolerating their passage. Faster transport, lower resistance, less voltage required to drive the reaction, less electricity consumed per kilogram of hydrogen produced. But the efficiency gain was only part of the story. The other part was durability. Conventional proton exchange membranes degrade. The acidic conditions inside an electrolyzer corrode their structure over time, reducing performance and increasing replacement costs. Boron-based materials are chemically more stable. They resist corrosion. They resist what the industry calls catalyst poisoning, the gradual contamination of the active sites that drive the reaction. The membrane lasts longer. The system performs better across its entire operating life, not just at commissioning. The result, after years of development, is a class of membranes that 1S1 describes as first of a kind. Stable, durable, superacid proton exchange materials that do not poison catalysts. And in tests with partners, electrolyzers running these membranes need just 70% of the energy required by incumbent devices to produce each kilogram of hydrogen. 30% less electricity. For an industry where electricity represents 60 to 80% of the total cost of production, that number does not produce a modest improvement. It restructures the entire cost model. In some cases, it is not the difference between expensive hydrogen and cheap hydrogen. It is the difference between a project that exists and one that never reaches a final investment decision. This is the part that should make you pause, and this is where most hydrogen stories usually fall apart. This one doesn't. Because this technology is not in a lab waiting for the next funding round. It is not a preprint. It is not a white paper with a promising model attached. This is already being tested in one of the hardest industrial environments on Earth. 1S1 is currently running pilots with an electrical utility connected to a major steel company in Brazil. Steel is one of the hardest industries to decarbonize. It requires extreme heat and chemical reducing agents, and hydrogen is one of the most credible long-term replacements for both. The fact that a steel-adjacent utility is piloting this membrane technology is not a coincidence. It is a signal about where industrial buyers are placing early bets, right now, with real capital. Beyond steel, 1S1 has announced a green ammonia project with a company called Nitrofix, backed jointly by the US Department of Energy and the Israeli Ministry of Energy and Infrastructure. Ammonia is one of the largest industrial hydrogen consumers in the world. The feedstock for fertilizer, for industrial chemicals, for emerging maritime fuel applications. Producing green ammonia at competitive cost has been one of the central challenges of the hydrogen economy. A 30% reduction in electrolyzer energy consumption directly attacks the largest cost line in that equation. The DOE target, 77% electrical efficiency by 2031, is already being met in these tests. 5 years early. With real partners, with real capital, in real industrial conditions. That is not a press release. That is a system entering its deployment phase. And if you have been watching the hydrogen industry for any length of time, you know how rarely those two things, the technology and the deployment, actually arrive together. But there is something even larger happening here that almost no coverage has touched. The boron membrane is not only useful for making hydrogen, and this is where the story stops being about an electrolyzer company and starts being about something far more consequential. The mechanism at the core of 1S1's technology, the ability to move charged particles selectively through an engineered material with precision and chemical stability, is not specific to hydrogen. It is a platform, and the applications extend into industries that most energy analysts are not watching. 1S1 is working with a large mine in Brazil to extract niobium. Niobium is a critical material used in high-strength steel and fast-charging batteries. The conventional extraction process uses powerful acids at high temperatures. It is energy-intensive, chemically hazardous, and environmentally damaging. The same electrochemical platform that moves protons through a hydrogen membrane can move metal ions through a mining process, selectively, cleanly, without the toxic chemistry. The same logic applies to gold. The standard processes for extracting gold use cyanide or mercury, chemicals that have caused documented environmental disasters across Latin America, including in Sobek's home country of Argentina. A boron-based electrochemical extraction method would eliminate that chemistry entirely. Step back from the individual applications and look at the pattern. Hydrogen production, green ammonia, steel decarbonization, clean mining, solid-state batteries, fuel cells. These are not separate markets. They are all expressions of the same underlying problem. How do you move ions through matter efficiently, selectively, and without destroying the materials doing the work? This is not a hydrogen breakthrough. This is a new way to move ions through matter, and that capability sits underneath some of the most important industrial processes on the planet. What 1S1 has built is a materials platform. Hydrogen is the first commercial application. The platform is the business. And the platform addresses problems that extend far beyond the energy transition into the physical infrastructure of industrial civilization. For anyone building content authority in clean industry, this is a second vertical hiding inside an energy story. The narrative does not end at the electrolyzer. It never did. And now we arrive at the part of the story that most coverage will not tell you. Because here is the uncomfortable truth. Even if every claim about this membrane is exactly right, even if the 30% efficiency gain holds at scale, even if the durability improvements are real, even if the cost projections materialize, green hydrogen projects can still fail. Not because of the technology, because of the system around the technology. You can't efficiency your way out of a system that doesn't run. Let's be precise about what the membrane solves. It reduces the energy cost of electrolysis. In a world where electricity is cheap, abundant, and consistently available, that improvement directly compresses the levelized cost of hydrogen. The math is clean, the economics improve. But the electricity is not always cheap, and it is not always available. The single largest killer of green hydrogen project economics is not the cost of the electrolyzer, it is utilization. An electrolyzer that runs at 40% capacity factor costs roughly twice as much per kilogram of hydrogen as one running at 80%. Not because the machine is different, but because the fixed costs are spread over half as many kilograms. A 30% efficiency gain on operating costs does not compensate for a 50% collapse in utilization. And utilization is determined by the grid, specifically by the availability of low-cost renewable electricity at the hours when the electrolyzer needs to run. Wind and solar are intermittent. The electrolyzer is not. Matching a variable electricity supply to a continuous chemical process without expensive storage or grid backup is one of the most difficult system design problems in the hydrogen economy. The membrane does not solve it. Then there is infrastructure. Hydrogen is not natural gas. It cannot move through the same pipelines without modification. It requires different compression, different storage, different safety systems. The industrial customers who want to buy green hydrogen at competitive cost also need it delivered reliably, in large volumes, at consistent purity. Building that infrastructure requires capital, permitting, offtake agreements, and multi-year development timelines that a better membrane does not accelerate. And then there is offtake risk. The most technically successful green hydrogen project in the world fails financially if it cannot find buyers who will commit to a long-term purchase agreement at a price that supports project finance. No membrane technology changes the risk appetite of an industrial buyer or a project finance lender. The technology improved. The system constraint did not move. A perfect machine inside a broken system still produces failure. This is the structural argument that the membrane breakthrough does not resolve. And it is worth stating plainly, not as pessimism, but as precision, because the developers who understand this distinction are building something different from the ones who don't. So here's the question that ultimately matters for everyone building in this space. If energy costs drop 30% at the machine level, who actually wins? Not the project that runs on expensive grid electricity with a spot market hydrogen offtake and no infrastructure partner. That project's economics improved on paper. It still doesn't work. Not the project that secured cheap renewable power but has no route to market. The machine running at 70% of previous energy consumption still produces hydrogen that has nowhere to go. The projects that survive and eventually dominate are the ones with three things locked simultaneously: low cost, high availability renewable electricity, firm industrial offtake from a buyer who cannot decarbonize any other way, and physical infrastructure that connects production to consumption at scale. What 1s1's membrane does is change the math for every project that already has those three things. It compresses the cost enough that projects which were borderline bankable become clearly bankable. It improves debt service coverage ratios. It makes the TKG number competitive not in optimistic scenarios but in base cases. That is not a small shift. In project finance, moving a project from borderline to clearly bankable is the difference between a final investment decision and cancellation. The developers who are closest to that threshold, who have already done the system work, gain the most from this breakthrough. The ones still hoping that better technology will substitute for system alignment will find that the gap has narrowed but not closed. In 2021, the DOE set a target that seemed ambitious: 77% electrical efficiency by 2031. A startup built by a bioimaging researcher and a materials scientist working at the intersection of microfabrication and electrochemistry hit that number 5 years early in real pilots with industrial partners. With applications that extend from green hydrogen production into clean mining and the decarbonization of some of the hardest industrial processes on the planet. That matters. It is a genuine breakthrough. Not hype, not a concept, not a policy announcement. It is a machine that works better than it was supposed to, sooner than anyone expected. But the lesson of hydrogen, the lesson that keeps proving itself in every cycle of optimism and disappointment, is that technology improvements are necessary but not sufficient. The machine getting better makes good projects better. It does not make broken systems work. So the question is no longer whether hydrogen works. The question is who built a system where it can survive. The developers and investors who understand that distinction, who are building at the system level, not waiting for the technology to solve what only system design can solve, are the ones for whom this breakthrough is actually good news. Everyone else just got a better machine. And a better machine inside a system that was never going to work still produces the same result.